So we're moving into gas laws now, and I want to start by trying to understand some of the variables that are involved in gas laws. The first one is probably the hardest to understand, and that is pressure. Do we really know what pressure is? Besides the weight of the world sitting on our shoulders, pressure is actually a measure of a force, and that force is caused by the particles hitting the wall of the container. So here's kind of a visual of what pressure looks like. You can kind of picture also that the more particles that you have, the more pressure that you will have. The more collisions with the walls of the container, the higher the pressure will be. So this is force per unit area. Yes?
Is there a difference between this kind of pressure and like when you're deep sea diving to that kind of pressure?
That's the same thing, same kind of pressure. So when you're deep sea diving, the reason you have pressure is because water is really heavy. If you ever really sat and thought and felt how heavy water is, like when you pick up a gallon of water. So that's why when you're underwater, there's a lot of pressure that you have to be concerned about. And that's why when you're underwater that deep, you have to be, anybody who's done scuba diving knows you have to come up slowly, because the gas that's in your lungs is going to expand. And if you come up too fast, you can die. And if you ever heard the term the bends, that's actually because air contains some oxygen that we need to breathe, right? But it also contains mostly nitrogen. What happens at a pressure that deep is that the nitrogen will actually dissolve in your bloodstream, and we can't use it. So like oxygen, we can use that in our bodies. We use it, we consume it, and then expel carbon dioxide. Nitrogen, we can't use it. So as you're coming up, those gas bubbles expand in your bloodstream. So it can be very painful. So much so that they started putting helium in scuba tanks instead of nitrogen, because we can't breathe in 100% oxygen. That would also be fatal to us. So it's kind of a tricky balance. Good thing somebody else figured out how to do this all, huh? It's a great thing about science, though. There's still plenty of things to learn. And if you're interested, still plenty of ways to make money. Look at what they're doing now. They're taking rich old dudes to space. Who would have known, right? Okay, so pressure can be measured in, we have a bunch of different variables that we can use. Pressure is one of those ones that more than one of them is applicable. So atmospheres are one of the units that we use usually, or millimeters of mercury. 760 millimeters of mercury is equal to 1 atmosphere. And also another one is kilopascals. There's our equivalency statements. We should be able to convert between these units. I want to point out to you what a millimeter of mercury is. So you're measuring the pressure in what's called a barometer. I don't even have a barometer in here. They took my barometer away from me because it had mercury in it. And they don't want us having mercury in school. So what this means, we know what Hg is mercury. What that means is the pressure that's pressing down on you and me, which is, in something that you can kind of understand a little bit more, 14.7 pounds per square inch. A square inch is like that big, right? 15 pounds on every square inch. Why do you think we don't feel that?
Like evolved to.
Yeah, it's always been there, right? So just like we don't know that we're hurtling through space really, really fast, we also don't know that there's thousands upon thousands of pounds of pressure sitting on us in the form of atmospheric gases. So that pressure that pushes down on us is also pushing down on this pool of mercury, and it will shove the mercury up until this tube, which has a vacuum. Who knows what's in a vacuum? Nothing. No gas particles. So when they say millimeters of mercury, they're actually taking a ruler out and they're measuring the height of the column of mercury in either centimeters or millimeters. So you're going to see centimeters of mercury or millimeters of mercury. That's what that unit means. So one of our variables is pressure that we're dealing with all the time. We'll erase that drawing. That was terrible. Another unit that we deal with that we're more familiar with is volume. That's the amount of space that it takes up. So volume would be kind of represented by length times width times depth, like such. How much space the gas particles are allowed to occupy. It doesn't matter what container you put gases in, they will fill their container. Gases are measured in either milliliters or liters. When we're doing the ideal gas law and using the ideal gas law constant, it's going to have to be in liters. And frankly, it's good practice. It's good practice to just say, I'm going to throw everything into liters, just because I want to be good at converting between milliliters and liters anyway. Our next variable is the amount of gas. And when we say amount in chemistry class, we're dealing with the number of moles. That's a count of particles. Remember, 1 mole is 6.02 times 10 to the 23rd particles. That's lots and lots and lots and lots and lots of particles. If you had a mole of dollars, or 6.02 times 10 to the 23rd dollars, every man, woman, and child on the face of the planet could spend $1 million an hour and there'd still be money left over afterwards. It's an astronomically huge number that it's super difficult to wrap our brain around. If you had 6.02 times 10 to the 23rd marbles, it would cover the earth 6 miles deep. It's impossible to try to wrap your brain around a number that big. That's why it always blows me away. All these, one guy's got all that money. You can't possibly spend that kind of money. So like a Jeff Bezos, all that money, there's no way he could possibly spend that money. It's just too much. So the number of moles can be represented by basically counting the number of particles. So just like 1 dozen is always 12, 1 mole is always a count of the number of particles, or 6.02 times 10 to the 23rd. So it's actually a way to count the particles. And our last one is temperature. And we got a new rule for temperature now. What is temperature really measuring? Do you know?
How fast the particles are moving.
So speed of the molecules. It's not measuring the amount of heat. It's measuring the speed of the molecules. So temperature would be, okay, if he's moving fast, he has high temperature. If he's moving slow, he has low temperature. But we've, up until this point, measured in Fahrenheit for most of our lives, right? And then we get to science class and we got to move on to Celsius. But not in gas laws. We have to use Kelvin. And there's a very specific reason why. Because you guys know, what's the freezing point of water in Celsius?
0.
So if you had something that was 0 degrees Celsius and you divide by 0 degrees Celsius, what do you get when you divide any number by 0? So that doesn't make sense. And especially it doesn't make sense to have a negative temperature, because if it's the speed of the molecules, you can't have a negative speed. Negative signs can only mean relative to something. So you can't really have actual negative quantities. So that's why we use Kelvin every single time. The temperature in all gas laws has to be in Kelvin, because there is no 0. Well, theoretically, there could possibly be one. What is 0 Kelvin called?
Absolute 0.
Absolute 0. Do you think we'll ever get there? We would have to violate some laws of nature, but who knows, maybe in a different galaxy, universe, who knows? I know I probably won't see it, but maybe you guys will. I never thought I'd see old guys in space, but here we are. So here's our 4 variables that we're going to be dealing with. Now let's talk about how they're related to each other. We're going to talk about relationships real quick. Whenever it comes to formulas, when we are doing math problems, anytime you have a formula where variables are divided by each other, they are directly related. Have the D's remind you of each other. That means as one variable goes up, the other one goes up, or as one goes down, the other goes down. So as expected, and you might have seen this before, if you have something that is, let's say you have a balloon and you take it outside and it looks like it's wilting, you bring it back inside, it'll plump right back up. So when gases get colder, they take up less room because they're not moving as fast. So the formula is going to be divided by each other, because the greater the temperature, the greater the volume will be. And if we heat a gas up, it will take up more room. This is why you can't throw like aerosol cans or pop cans in a fire, because you can cause an explosion. Let's go to our next scenario, which is pressure and volume. When things are multiplied by each other in formulas, they are not indirectly but inversely related. Inverse means that as one goes up, the other goes down. So as expected, if you pressurize something, it will take up less space. So if you can think of sitting on a balloon, or if you've ever taken bubble wrap and squeezed, you're going to pressurize that bubble of air and eventually it will pop. So our other relationship, that's not right, is pressure and volume are inversely related to each other. So let's combine those, and we get the combined gas law. We're going to add one more concept into here, is that the more moles of gas you add, the greater the volume. So if you can think of blowing a balloon up, as you blow into a balloon, you are forcing more moles of gas into that balloon. So the last step in this particular introductory discussion is to combine these all, and we're eventually going to derive the ideal gas law from this. And that will be our next lecture. But we do need to know P is for pressure, V is for volume, T is for temperature, N is for number of moles. Pressure is inversely related to volume, but directly related to temperature and number of moles. Volume is inversely related to pressure, but directly related to temperature and number of moles. So if two things are multiplied in a formula, they are inversely related. That means that you can expect as one goes up, the other goes down. If they are divided by in a formula, you can expect as one goes up, the other one will also go up.